All right, let's do an example for Newton's law of cooling with the new feature that we can now handle. So let's say you've got an object in an environment. The object has a temperature, T, and the environment has a temperature, TE. And let's assume that the environment progressively gets hotter in kind of a linear way. So the temperature is just increasing linearly. So let's assume that the environment temperature is not a constant, but starts at 0, so TE of 0 is 0, and then it just increases in time at a rate of one unit of temperature per unit of time. Then Newton's law of cooling says about the object's temperature that the object's temperature obeys this differential equation. Its derivative with respect to time, d capital T d little t, equals minus h t minus te, except this is now little t. And I claimed before that this is a linear differential equation. It's not separable, but it is linear. And to see that it's linear, we should write it in the standard form. So I can add, I've got a minus ht plus h little t here. So let me add this to the other side, and then here I have h little t. So there you can see it's unknown function plus function of t times unknown function, although this is a constant, but still, equals function of t. So this constant is playing the role of p of what I usually call p of t, and this one is playing the role of what I usually call q of t. All right. So how do we determine the behavior of this thing? And let's throw in an initial condition just to make this more interesting, I guess. So we've got the temperature starting, the environment temperature starting at 0 degrees, and the object temperature, let's make it also start at 0 degrees. And then the environment temperature will increase sort of by 1 degree per unit of time. And the object temperature should also increase along with it, right? Like as the environment heats up, the object, initially when the environment starts heating up, the object will become colder than the environment. So the environment will heat up the object. But that takes time, so there's going to be a delay, kind of. The object is not just going to always have its temperature equal the environment temperature. There's going to be some kind of delay, and the delay has to do with this constant, little h, which governs sort of how quickly the object and the environment exchange heat. All right, so it's going to be interesting, I think, to see what is the functional form that we end up with for the object temperature. So we need to use the method of integrating factors here. And so we need an integrating factor, a mu. And what does mu have to do? Mu has to make it so that this thing is the same as the derivative of mu. So we want this to equal mu prime, or d mu dt. So that's the point of mu, is that d mu dt has to equal mu h. Okay, do we know of a function whose derivative equals itself times h? Of course, this is a separable differential equation, and I can use separation of variables, but we could really just skip to the answer. It's just e to the ht, right? That's the function whose derivative is h times itself. So there, we've got our integrating factor. So now I'm going to write e to the ht, t, plus e to the ht times h, t, equals e to the ht times h, little t. And now I can notice that this is actually ddt of e to the ht, t. A product rule has been applied to take this derivative and give us this. Now we can integrate, so e to the ht t equals, and this is kind of annoying, so let me pull out the h. Let me write it in this order. Let me pull out the h. Now I have to integrate t times e to the ht with respect to t. And after I do this integral, I can throw in the plus c, but let me just throw it in now so I don't forget. Yeah, so this is going to be kind of a pain. This is not such an easy integral to do. And it's totally fine to use Mathematica or Wolfram Alpha or whatever. Okay, so you can just use Mathematica, but for fun, I'm just going to show how to do the integral. So this one you have to do integration by parts, which is basically like rewriting this sort of as one of the two terms that you get when you write a product rule. So I don't know if you noticed, but I paused the recording, and then that gave me a lot of time to think about how I'm going to set up this integration by parts. Then I resumed recording. So I just paused and got a chance to think about this. I'm not just doing this off the top of my head. This takes some effort. So this thing here, te to the ht, is the derivative with respect to t of this product, te to the ht over h. Sort of, not really. If you take this derivative, then you have to use the product rule, and one of the two terms is this one, but the other term is an extra, so we have to subtract that off to make this equation true. And that other term is this, e to the ht over h. And so this integral, te to the ht dt, is the integral of the derivative of te to the ht times 1 over h minus e to the ht times 1 over h. And all of that is the integrand. And now the integral of a sum is the sum of the integrals, and the integral of the first portion is the integral of a derivative, so you get right back to te to the ht times 1 over h. And for the second term, now that's something we can actually integrate. So the integral of e to the ht is 1 over h e to the ht. So I should get te to the ht 1 over h minus 1 over h squared e to the ht. And this is what I get for the integral. And just because I'm not too confident about my calculation, let me go check that in Mathematica. Okay, here we are. So I'm integrating te to the ht. With respect to t. And let me expand that so it looks more like what I've written. So let's see. Trying to put everything on screen at once. Here, I've got te to the ht over h, that's this term, minus e to the ht over h squared. Ah, good. Okay, now I can continue the calculation from the beginning. So e to the ht t equals, and then I had an h here multiplied by this integral. So that's going to cancel some of the h's in the denominators here. So I get te to the ht, and that h is gone, minus, and then 1 over h rather than 1 over h squared, e to the ht. Of course, and plus c. And it's important to keep that c there before we multiply by e to the minus ht to isolate capital T. Because that's where all the time dependence shows up. So now we can finally multiply by e to the minus ht. Well, actually there's time dependence here also in this t. We get t minus 1 over h plus c e to the minus ht. And that is apparently how the temperature evolves in time. Well, that's the general solution with this parameter c. So it's a whole family of solutions. But if I want the particular solution that satisfies... Well, I forgot to write down the full initial condition. I want the initial condition t of 0 equals 0. I think that's interesting, where the object initially has the same temperature as the environment, which is 0. The environment has temperature 0 at time 0. And the environment temperature is ramped up, and we want to watch the object temperature try to catch up to it. So let me put in that initial condition. So 0 is t of 0 is what I would get here if I plugged in 0 for t, which is minus 1 over h plus c. So c must equal 1 over h. T minus 1 over h plus 1 over h e to the minus ht. And I don't know about you, but I really want to plot this. I just want to see what shape that has. What does it look like for the object temperature to try to keep up with the gradually ramping up environment? All right, so let's plot it. So what should be interesting actually is to plot two functions, the environment temperature and the object temperature, and see what they look like together. So I've got the environment temperature is just T, and the object temperature is T minus 1 over H plus 1 over H e to the minus ht. And by the way, in case you're using Mathematica, I'm always putting a space here between variables when I'm multiplying them. If I don't put a space, then it'll treat that as one variable with the name ht, but it should be h times t. All right, and if I plot this, actually I'm going to get nothing because Mathematica doesn't know what h is. But one thing I can do is just say h equals 1. Let me just pick something and look at what the plots look like. All right, so plot, and if I remember correctly, I think I should be able to just list the two functions in a curly braces list. And we'll plot from time equals 0. How about for 4 units of time or something? Let's see what that looks like. Okay, interesting. So I guess the straight line here, the orange one, that's our environment temperature. And then the blue line is our object temperature. And you can see they both start the same. They start at 0 degrees. And the environment temperature just ramps up linearly. And the object temperature tries to keep up. But it's always behind by some amount, right? The environment temperature sort of started without it. The object temperature is always behind by some amount. And it almost looks like it's behind by a constant amount all the time. So that's, or not a constant amount, but the amount by which it's behind looks like it's approaching something asymptotically. So I guess that makes sense. If you look at the difference between the environment and the object temperature, like T minus T sub E, what would you get? I think you would get T minus T sub E is that thing minus little t, right? Because this is little t. So you just get this. Which, as time increases, this approaches, this decays exponentially, so this approaches minus 1 over h. So the gap size that we should expect here is, initially it's a gap of size 0 down here, because they agree, the object and the environment temperature start the same, but then the gap size approaches a gap size of 1 over h. And we set h to 1, so the gap size is approaching 1. And it looks, if I look at the axis here, it looks like, yeah, that gap size is about 1. Another fun thing we could try is look at the effect of h on things. So let's manipulate this. Manipulate h. So let's vary h from 1 to 2. 1 to 3, how about? Well, I guess I cannot vary h because I already set it to be 1. So let me reset h here. Okay, that's not behaving the way I expected. I think it makes a lot more sense to make these also functions of h, so that the h dependence of the plot is clear. There we go. Okay, now as I vary h, so as I increase h, that's interesting. The gap closes. I guess that's what you would expect, right? If the gap size is 1 over h, as we found back here, you would expect as you increase h that the gap will shrink. And that should make some physical sense, because in original Newton's law of cooling, what was the role of h? In the original Newton's law of cooling, h is the proportionality constant that tells you how fast the temperature tries to equalize to the environment temperature. So yeah, if you increase that, then the object temperature will have a better chance of catching up to the environment temperature. So here's a fun problem on your homework where you've got the temperature inside a house and the temperature outside the house varying. So instead of the environment temperature simply being T, just ramping up linearly like I was doing, you've got something way more complicated. And it's varying and it's oscillating, actually. So this will be pretty fun, watching the environment temperature oscillate and then seeing how the temperature inside the house tries to keep up and equalize as the outside temperature is constantly changing. However, one not so fun aspect, depending on your relationship with integrals, is that you would have to look at this integral, an integral of e to the t cosine t, or something like that. And that's actually quite a bit harder than even the integral I did here. Here I have t times e to the ht. You'll have something like cosine t times t to the ht. So I suggest you can use Wolfram Alpha or Mathematica. Mathematica is, Wolfram Alpha is basically just using Mathematica behind the scenes. Or if you enjoy integrals, go ahead and check out the trick that I linked you to over here. You can do it using integration by parts, but it will require doing integration by parts twice and then writing down some equation. But yeah, what I'm trying to tell you is there's no shame in using an integral calculator of some kind to help you with the integrals. Since this course is not Math 3B, I'm not trying to teach you about integrals. So there's no shame in that. But there is some shame. You should feel a little bit guilty if you just use a differential equation solving tool, or if you ask Mathematica to just solve a differential equation for you, because then you might have missed the point.